In this video, I want to talk about the physical difference between total derivatives and partial derivatives by looking at a specific example. So let's say that we know the temperature in a three-dimensional room, capital T. So this is going to be a function of the three variables, x, y, and z. And let's say that it also varies throughout the day. So it's also going to be a function of time, little t. Now, the partial derivative of the temperature with respect to time is taken by assuming that x, y, and z are constants, and then you differentiate with respect to t. So this represents the rate of change of temperature at a specific point in space in the room. So, just as an example, so let's say that if t is x plus 2y plus 3z plus 4t, then the partial derivative of temperature with respect to time is going to be just 4, because x, y, and z are constants, and this is how we take the partial derivative. So yeah, again, this is the rate of change of temperature at a specific point in the room. All right, so now the total derivative of the temperature with respect to time, how is that different? So when you see a total derivative, this is just automatically you assume the function that you're differentiating is only a function of one variable. So when you see this, automatically t is only a function of time. So this is going to be so t is a function of x of t, y of t, z of t, and t, like this. So to write a formula for the total derivative of temperature with respect to time, we use the chain rule. So this is going to be partial derivative of capital T with respect to x times dx dt. And then we continue, partial derivative of t with respect to y times dy dt, plus partial derivative of temperature with respect to z times dz dt, and then plus partial derivative of temperature with respect to time times dt dt, and this is just 1. So these first three terms can be interpreted as the dot product of two vectors. One is the gradient of the temperature, so partial t, partial z, and then dot it into a velocity vector, dx dt, dy dt, dz dt, and then plus partial t, partial t. And so very compactly we can write this as gradient t dotted with the vector v, the velocity vector, and then plus partial capital T, partial little t, like that. So what does this mean? So yeah, so when we have x of t, y of t, z of t, that means that you have the position of something that's moving in the room as a function of time. So let me just draw a box here just to illustrate. So let's say that there's a housefly in this room that we know the position of. So it moves around the room according to r of t, a given position vector. So this is going to be x of t, y of t, z of t. So our interpretation of the total derivative of temperature with respect to time is going to be the rate of temperature is going to be the rate of change of temperature that the fly experiences as it moves throughout the room according to its position r of t. And this is going to be the formula. So not only does the rate of change of temperature that the fly experiences depends not only on what the rate of change at at the fly specific point, at the at the rate of change of temperature at a specific point, but also on the component of the fly's velocity in the direction of the temperature gradient. So I think that's interesting. That is the so that's going to be, so again, that's the total derivative is going to be rate of change of temperature that the fly experiences as it moves throughout the room. Yeah, so hopefully that gives you a better understanding of the difference between total derivatives and partial derivatives.